Hello, my name is Gertjan Berghaus. I'm with the Intelligent Imaging Department at TNO. My work is to develop autonomous systems and to analyze images to take actions on those platforms. Here you can see a drone, and we see that more and more of these applications become actually moving platforms with AI on top of it to be autonomous. Here our drone was getting into a foggy area. When platforms move, it means that they can also get into unexpected situations, like fog. Here, our drone didn't know how to deal with those images, and it detected all kinds of objects which were actually not there, which you can see over here in the bounding boxes in these foggy places. This led to an undesired result, because the drone didn't know what to do anymore. This is especially true for deep learning, that when it encounters unexpected situations, it may behave badly. That is because of two reasons, as this paper shows. It depends on both two operations that are within the deep learning framework, like the ReLU and the softmax, which enforce the network to be confident always, also in the case that it is not reliable anymore. In this case, our drone had no idea that it messed up. All of these bounding boxes, it didn't know that there were no objects there. And the question is how to solve this. So we built another platform. Here you can see our autonomous vehicle. It's a robot car. And we built a task on top of it, which is to monitor a building to find people. For instance, when it's late at night, no people should be there anymore, and it should inspect all of the places within the building to see whether there are still people around. As a very common way to do this, we took an object detector, in this case the SSD, the single shot detector, and we put it on this platform to see whether it could find any people. It encounters situations like these, so corridors and lab rooms, because this is in our building. Actually, this is a dataset from Fukuoka, but we wanted to test it for situations like very similar in our research building. We saw that the model was performing very well in these corridor environments, but it performed very badly in these lab rooms. The model apparently was optimized for people who stand up and are mostly visible, so really pedestrian type people. It was not optimized for sitting and being only partially visible. Well, of course, the detector can be improved by also detecting those people in those poses, but that was not the goal of our research. We wanted to take the model as is and wanted to know whether it was reliable in particular situations or not. So how to go about this? Well, so we had this robot car, we had a single shot detector model. We found out that it was actually optimized for people standing up because we knew the dataset where it was trained on, but usually we don't know that. So the model is really a black box. We don't know its parameters and we don't know what it was trained on. Now we go to these situations and we want to know whether this robot car with its AI model is competent here. And also in the other situations, like the lab room. That's why we thought of a competence assessor, which is like an external process that monitors the AI model to see whether it's competent or not in particular situations. And at the end of my presentation, I have a demo to show what we achieved. This competence assessment is actually a function of a task, a situation, and a model. The task was to find people in the building, but it can be a different task, of course. The situation was whether it was in a corridor or in a lab room, and the competence was, is it performing well or not? And the model was actually producing these results. So it's a function of task, situation, and model, and our goal was to assess from that the competence. We wanted to do that with an external process because the AI model itself doesn't know where it's competent or not. There's a whole bunch of interesting research going on right now to assess that, but we wanted to take the model as granted and to see what we could analyze from there. The robot might say, I don't know this situation the first time because it's a corridor which it didn't see before. So it also cannot assess the competence. So it needs to rely on some external source. That might be some knowledge graph, for instance, but we solved it simply by having an expert saying whether the robot was competent or not, based on the detections it saw on the images displayed. Then the human could say, yes, the robot is competent here because it could see good detections there. And then the robot should be able to generalize also to different kinds of corridors as shown here. That means that we need to reason about situations like these and to generalize or not to generalize. So we took the MIT Places dataset as a starting point for environments. There's a whole bunch of environments in there, and we can use it to compare environments among each other. So we know whether situations are the same or not. Here you can see that in the corridor, yes, they are all the same, and we want the robot to analyze and to generalize that it should be also competent there because it's similar environment, so that the human doesn't need to provide his or her feedback at every time. So we took those MIT places as a way to consider whether environments are similar or not. And then the robot should be able to generalize that it doesn't know this situation because it's really different. A lab room is very different from a corridor. So it should say, this is unknown to me. And then we could invoke the human again to ask it for human assistance and for feedback about its competence. And so the human could say, you're incompetent here. And then the robot can generalize also to other lab rooms to know that it's also incompetent there. That's a very important step, because if the robot is able to do this, to say whether it's competent or not, then it also knows when it is reliable or not. And for instance, when it's not reliable, it can invoke the human for assistance. For instance, I'm not competent here. Can you look whether there's any people present in this room? Because its task was to find people in rooms. And it knows it cannot do that in lab rooms, so it needs the human assistance. This is the movie of our demonstration. So the robot starts driving through the building. At first, it doesn't know anything, so it needs to learn about environments. Here you can see what happens. The robot says, I don't know anything, so I'm going to collect images from the MIT Places dataset. It contains a lot of images of various types of environments, like you can see here. It embeds those environments based on similarity. So here you can see buildings closer to buildings and parks closer to parks. So it gets a sense of how different various environments are. Here it enters the corridor. It doesn't know it, and it asks the user, am I competent here? The user says yes. Here you can see that the robot starts to generalize because it also knows that it's still the same corridor, even though the lighting changes a lot and there's posters on the wall. The robot drives around the corner and enters the lab room. Here it doesn't know the environment. The user says, you're not competent here, based on the fact that there were people inside that it didn't detect. So the robot starts to drive. It now knows the environment, but it knows it's not competent. It makes a second round later, and now it knows the corridor. It doesn't need to invoke human assistance because it does know about these corridors and how they look. And when it enters the lab room, it also knows that environment, and it knows it's not competent there. This is really important because knowing that it is not competent here, the robot can ask the human for assistance. I think this is a very step forward to having robots that understand when they are reliable or not, and when they know they are not reliable, they can ask a human for assistance. Thank you for your attention. Have a nice day.